Okay, I think we're back. All right. So we've already built the matrix SZ. So let's go ahead and build the matrix SX. By the way, it's probably a good idea. It may be a good idea to run all of these cells. So we're going to do runtime, run all. And this should run all of the cells from the beginning, and then it's going to break once it gets to this cell because we haven't actually written this code. But hopefully everything up to this point is working. So good. Okay. All right. So let's go ahead and write the code to define SX. And we already have hbar stored from our previous block, so we don't have to define it again. So we'll write hbar over 2 times np.array, open brackets, open brackets. And now for SX, I have row 1 is 0, 1. So I will write for row 1, 0, comma, space 1. That space is not necessary. I just like to have a little space. And then outside of that, first close brackets, I'm going to put a comma to start the next row. Then I'll open brackets again for that new row, 0, comma, minus 1. Close brackets, close brackets. Oh, that's not right. I did that wrong. Sorry about that. What should I write for the second row? Thank you. 1, 0. Excellent. Okay. SY. So SY looks a little weird, right? It's got these imaginary units in it. But here's a little note. How do you get the imaginary unit? The syntax in Python for the imaginary unit is the number 1 and then the letter J. So this would be another sort of name that you should avoid for variables. If for some reason you wanted to call a variable 1J, that would be a bad idea, for the reason that 1J already has a value in Python, which is the imaginary unit. Okay. Okay. So now I have for SY, hbar over 2 times np.array. First row is 0 minus I. Second row is I, 0. Does that look okay to everybody? All right, and let's print. And this looks about as I would expect it to. SX, 0, 1 half, 1 half, 0. And then SY is 0 minus 1 half I plus 1 half I, 0. I'll just point out with SY, you'll notice that all of a sudden, all of the numbers in SY have both a real component and an imaginary component. And so this is a sign, if we were to, for example, I remember we talked about data types. If I do print np, or if I do type SX, so print type of SX, and print type of SY, I should see that, no, what if I do np dot? Is that better? Nope, that's not one. I think I have to access an individual element. Sorry. Okay, type of entry 0, 0 of SX, that's the number 0 here, and entry 0, 0 of SY, that's the number 0 here. Those types, I should see float, No. Okay, yeah, float 64 and float complex 128. So SY stores complex numbers and SX only stores floats. And the reason why is Python or NumPy decided an array of complex numbers because some of the entries I have defined to be to have imaginary components. And I only wrote real components for SX, so NumPy has decided that this should be an array of floats. And then the other thing, we had a little discussion in one of the labs, I think maybe Wednesday lab, about precision. So actually, this is, if you want to know something about the precision that you can represent these numbers, this is actually giving you a hint. So this is telling you that each of the floats is represented by 64 bits by 128 bits, which should be equally spread among the real and the imaginary components. So each real part of the complex has 64 bits, and each imaginary part of the complex has 64 bits. Okay. So now, all right. Here's going to be the real test about the properties of SX and SY. What we're going to do is we're going to take our kets from before, right? We had ket alpha and ket beta, where we have already confirmed that ket alpha was an eigenvector of the matrix SZ, and we have already confirmed that ket beta was an eigenvector of the matrix SZ, right? We did that in one of our previous Python selves, and then we just did it on the board. So now what we're going to do is we're actually going to see if those kets are also eigenvectors of Sx and Sy. And what do you all think is going to happen? Are we going to find that they are eigenvectors or not? Raise your hand if you think, yes, they're going to be eigenvectors of Sx. Raise your hand if you think, no, they're not going to be eigenvectors of Sx.
Anyone raise your hand?
Yes, there's a few hands raised. Let's do a proper vote. I'm going to tally the results. So we're going to find out. So one of the things, so hopefully from the first Stern-Gerlach experiment, poll that I did, you can appreciate it's okay to be wrong in this class because none of you know the answers to these questions. I should say, people that haven't studied quantum mechanics would not know the answers to the questions about the Stern-Gerlach box. Now, hopefully now we have a little bit more information about this question, but it's still okay to be wrong. Okay, so the question is ket alpha, which is equal to 1, 0, on eigenvector of Sx, which is equal, the matrix Sx, which is equal to h bar over 2. How did I define it again? 0, 1. 1, 0. Yeah? I hope I have done this right. I feel like there should be a minus sign here, but we will find out. Okay, so is ket alpha an eigenvector of this matrix? A is yes, B is no. Think about that for a minute while I double check because I feel like there should be a minus sign somewhere in this Sx matrix. There's not. Look at that. By the way, the sort of un-h bar over spin matrices if you want to look them up. Okay. All right, great. So we're back. Let's take our vote. So raise your hand if you think yes, vector of the Sx matrix. 1, 2, 3, 4, 5, 6, 7, 8. Okay, 8 and no, they're not. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, 9. Oh my gosh, we're like split. So we can do let's figure out how we want Well, how are we doing on time anyway? Still have 40 minutes. We can approach this in one of two ways. We're going to do it empirically, where we just finish this code and we find out, or we can argue it out. What would you all prefer to do? Empirically or argue it out? Okay, empirically. Thank you. So let's do it. So we're going to compute the product of Sx and ket alpha and store it to Sx ket underscore A, like this, and then print it. Do the same thing for Sx ket beta, store it to Sx ket underscore B, print it. And do the same thing with Sy on ket beta and ket alpha. This is a typo here. You should store Sy on ket alpha to Sy underscore ket A and print it. So I'm going to intentionally mute my screen now for the first time today. I don't know why this keeps happening.
Because you have a Mac.
I don't know. It might be. I think there's just a little bit of like, tension on this thing.
Aren't there multiple people that are not in lab? I'm like down to.
Good question. I actually did not take.
Yeah, you're missing a few people, but I think the lecture people are caught up from where the lab people are. She had a couple issues, but we fixed it.
Okay.
And then I told Julius to just start from the beginning, and then because he's gonna be behind.
Okay. Yes. I told him I would send the videos.
And remember, if you have any issues, or if you're doing good, have your green sticky up. If you're having issues, put your pink, or for those of you that bring it out, just hide your green.
All right, so I'm going to clear the results here. So it seems like most people are got their green stickies up. So wait another minute or so, and then let's take a vote. Oh, you do have the double parentheses, yeah. That must make a difference.
That's well, that's how
Perfect,
I
yeah.
managed her
There's a, yeah.
when I
There's
accidentally
no problem.
Oh, because you had that.
Yeah.
Yeah, okay. So you were able to fix it.
Yeah, I got that's control.
No. Oh, sure. Okay. Let's see. So you printed I see SX there, and then, oh, okay. This, the reason we've got an error is those parentheses on the array should be square brackets. So that, I understand, that's very hard to see that those are square brackets. Right there, yeah. So basically, I'll make a remark about this because it's not really obvious. And then same thing there, yeah. With SY, change those parentheses to square brackets. Okay, perfect. That works.
What's a typo over here? This should be an A.
Yes.
That's what I was telling you, but it was a copy paste.
It was a copy paste issue, yeah. Yes. Yeah, just to point out, if you're going through all of these, the product of SY and ket alpha should be SY underscore ket underscore A, not B. And I will also point out one other thing, that we've been using open parentheses quite a lot, like the rounded parentheses, and then we've also been using brackets, and I have not really carefully explained when to use one and when to use the other. So the rounded parentheses, open and closed, will always accompany functions. So if I dot array, that's an actual function. Print is an actual function. Conj, np.conj was an actual function. So those will have rounded parentheses. And then arrays have square brackets that enclose their elements. And so what the syntax down here, right, I'm actually mixing two functions here. I've got print, open rounded parentheses, and I'm closing the rounded parentheses on the other side of print. And then type is another function that tells me what type of data is enclosed. So that's got a rounded parentheses, and this has a rounded parentheses. And then I'm asking specifically about one element of the SX matrix. And so this is element row 0, column 0, which is this element right here. This is, in Python's way of counting, this is row 0, column 0. And this would be row 0, column 1. This will be row 1, column 0, row 1, column 1. Python starts counting from 0 with arrays, which causes a lot of humans to short circuit for a moment, including me. I'm trying to think. There's 3 programming languages that I'm somewhat familiar with: C and Fortran and Python. And Python and C start counting from 0, and Fortran starts counting from 1. And usually humans also start counting from 1. And anyway, so that's just the nature of this nomenclature. Okay. Is everybody okay so far with with these matrix vector products of SX, ket alpha, SX, and ket beta, SY, ket alpha, SY, ket beta? Okay. Let's go ahead and retake our vote then. So what's the conclusion from our empirical experiment? Ket alpha, an eigenvector of SX, yes or no? Raise your hand if you think the answer is yes. A few of you. 1, 2, 3, 4. And no. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, so most of you vote no. And a few of you vote yes, and actually I can sort of understand why this isn't crystal clear. All right, so what has actually happened to chi alpha? So chi alpha, right, SX, what happens to it? What is this telling you? This first result is SX on ket alpha. which direction is it pointing after the multiplication? To the right, yeah. So the result essentially is a rotation, right, and a contraction. So it was pointing up along this axis, which we're calling alpha hat. And then after multiplication by Sx, it is pointing along the direction b hat, or beta hat. So is it an eigenvector? No, it is not, because it has changed directions. And we see that actually happens with all of them. So this one was the result of Sx on chi beta. So basically the sort of conjugate process happened with, so this is sort of what Sx on 1, 0 did, right? It gave us h bar over 2, 0, 1. And then, which looks like this. And then Sx on 0, 1 is going to give us h bar over 2, 1, 0. Okay, which is going to look like this rotation. Start out pointing along beta with magnitude 1, and then I rotate to point along alpha with magnitude h bar over 2. Okay. So everybody fairly clear with that? All right. All right, and so the same thing happens with Sy, except for a little bit weirder, right? So Sy on chi alpha, what it does, we can no longer sort of capture what it does with this two-dimensional axis, right? Because has like a real. This is only real, this is only real. And what's happened is I've actually sort of like rotated chi alpha out of the real plane into the imaginary plane, right? So it has, it's no longer pointing along plus real alpha, it's pointing along, I guess, imaginary alpha. And the same thing for, it rotates it out of the real plane into some imaginary axis. So this is all to say chi alpha and chi beta are not eigenstates of Sx or Sy. And again, this shows up in the Stern-Gerlach experiments. If I send silver atoms in eigenstates of Sz into a box that measures Sx, I do not have a definite result. There is two possible outcomes. If I send that same eigenstate of Sz into the Sy box, there is not a definite result. There are two possible results. Okay, so the last question, what do the eigenvectors of these matrices look like? So we've sort of answered these questions, by the way. So let me just take a minute to say, what will you submit to us? So your completed notebook and answers to these questions. Okay, and so the way that we strongly prefer that you answer these questions is within these cells. Okay, so where the question is, you can double click and you can start writing your answer. So let's practice writing the answer together because we have already answered this question together. After inspecting the results of each matrix vector product, do you think the basis kets, which are chi alpha and chi beta, are eigenstates of Sx and Sy? So I'm going to say no. We see that the result of multiplying the basis ket, and I'm going to write the math font. I'll do it slowly so you can see the syntax. You don't necessarily have to do this. It's totally sufficient to say the basis kets. We will know what you're talking about. But the math font, which you can copy from above if you want, chi underscore bracket alpha superscript. Oh, these are, I'm sorry. Wrangle. That's what I wanted. And same thing. So all of these Greek letters, by the way, you get the Greek letters in these cells by being in math mode, which means you have open $, closed $, around it, and then this / and the name of the Greek letter. So this, I keep calling this chi alpha. Why I call it that? Okay. So I can get that Greek letter, but it's also totally sufficient if you just want to say the basis states, or the basis kets, because we will know what you're talking about. No, we see that the results of multiplying the basis kets chi alpha and chi beta, rotate them and change their length, which means they are not eigen states of math B S X or math B S Y. So again, I'm in math mode because I've opened $, closed $, and this is just a little formatting that gives this lovely Blackboard bold font to S, and which is one way to signal that you're talking about a matrix. So that would be an adequate answer to question 1. Question 2, I'll leave for you all to do what is the shape of the result of each matrix vector product. So we did go through taking shapes earlier on in the notebook. So you can take the shape of these kets and print them, and then just write the shape here. It's like, basically like the shape is, tell me what the shape is. Okay. So any questions about how to answer those questions in these cells? Do I expect you to format your math nicely? No. If you please, totally fine to just answer with plain text. Okay. All right, so let's move on to so this is the last thing that I'm going to talk about, because it is sort of the last new piece of syntax, and then we'll be done with the instruction piece, and you still have a few more questions, but it's all using the same syntax we have used already, and also the syntax is repeated in the markdown cells for your convenience. So let's do the last. So basically the question here is, well, if this ket alpha, or ket chi alpha, is not an eigenvector of Sx, and it's not an eigenvector of Sy, well, what do those things look like? What do the eigenvectors of Sx look like, and what do the eigenvectors of Sy look like? So we can use Numpy to tell us that. So Numpy has this package, this sublibrary called linalg, and we have already imported that. Remember, we did from Numpy import linalg as LA, and one of the functions in the linalg package is called eig_h, And IH will take a matrix and it's going to return two different NumPy arrays. It's going to return a NumPy array of its eigenvalues, and it's going to return a NumPy array. Okay, and so we'll use that, and we'll call it on the matrix SX, and we'll call it on the matrix SY, and then we're going to print the eigenvalues and the eigenvectors, and also the shapes of those eigenvectors and eigenvalues. Okay, so this is the syntax. You have an assignment kind of statement, right, where I have eigenvalues, comma, eigenvectors is equal to la.eigh on my matrix M. And so I'm just going to do that with where I'm going to substitute Sx for M, and I'm going to substitute vals x for eigenvalues and vex x for eigenvectors for my matrix Sx. So then I will store the eigenvalues of the Sx matrix to vals x, and I will store the eigenvectors of the Sx matrix to vex x. So I'll do vals x, comma, vex x is equal to la.eigh as z, no, not sc, sx. Okay. And the same thing for y is equal to la.eigh sy. How do I print the shape? Anybody remember? Yes. Print np.shape vals x. Print np.shape vex x. Okay. I'll also just add, if you're finding yourself getting a little bit overwhelmed by these lines of numbers over and over and over again, which I myself do, you can feel free to add in a print statement above each line that says, like, this is the shape of vals x. Print this. This is the shape of vex x. Print these are the eigenvalues of Sx. Print these are the eigenvectors of Sx. These are the eigen of Sy. And print these are the eigenvalues of eigenvectors of Sy. And then you'll at least have a little bit of text above each line that reminds you what these things are. Okay. Yeah, oh, no, I don't think so. I can't remember if I put it in Canvas or not. This will be due next Friday at the end of this problem solving session. So approximately 1 week and 15 minutes from now. And you'll submit that through the 3141 lab Canvas page. Except for these that are only in lecture, you can just email it to me. Email me the link. Thank you. Anybody still working on this? Are we okay?
Oh, I have a question. So, for the first one, is this, saying that it's a row of two?
It's two rows.
Oh,
Yes,
two rows.
2 rows. Although it seems actually at odds with what we have, because it looks like we have two columns. 2 rows. 2 columns. Yeah, I'm confused by that actually. The eigenvalues have just 2 rows, but then when we print, it looks like it has 2 columns. But anyway, let me at least say one thing for sure. There are 2 eigenvalues. Each eigenvalue is just a number. It's a scalar. So we have one scalar which is -1/2, one scalar which is +1/2, right? And so those eigenvalues are exactly the same as the eigenvalues of SZ. When we look down to the eigenvalues of SY, exactly the same, -1/2 and +1/2. So SX, SY, and SZ all have the same eigenvalues. So the possible outcomes of measuring SX are plus and minus 1/2 h bar. The possible values of measuring SY are plus 1/2 and minus 1/2 h bar. And the outcomes of measuring SZ, as we already saw in lecture, are plus 1/2 h bar and minus 1/2 h bar. So each observable of spin has the same range of possible outcomes. But the eigenvectors are all different. Okay. So here's what we have. We have an eigenvector for Sx associated with this eigenvalue, which is this crazy number and this crazy number. That crazy number, by the way, I don't know if this will just jump out to anybody, but I'm going to call this first eigenvector of Sx. I'm going to call it chi beta of x. Why chi beta of x? Because it is associated with the x component of spin with eigenvalue minus 1/2 h bar, just like chi beta of z was associated with the eigenvalue minus h bar over 2 along z. Okay, so this number here happens to be minus square root of 1/2. And this number here happens to be plus square root of 1/2. You can double check if you don't believe me. I do, of course, make mistakes. So these are these coefficients, but what goes after these coefficients? Well, it is actually the basis kets, which are the z kets. Okay, so in other words, what we can essentially say, right? So we have built S of x in exactly the same basis as we built S of y, right? In the basis of are eigenkets of SZ, which their vector representations look like 1, 0, and 0, 1. Okay, so we can think of this as, we can think of this ket beta along x as another column vector where its values are given by minus square root of 1/2 times the column vector associated with chi alpha, which is 1, 0, plus square root of 1/2 times the row vector, times the column vector associated with chi beta, which is 0, 1. Okay? So then how does this work out? I've got this is equal to this number times this vector, right? So I get essentially a new column vector with, that looks like this, right? I multiply 1, 0 as a vector by this number minus square root of 1/2, and I get a new vector minus square root of 1/2, 0. Okay. And then I have a second vector, right? 0, 1 times the number square root of 1/2, which gives me 0 square root of 1/2. Okay. So I'm going to add these two vectors element by element, right? Row 1 of this vector plus row 1 of this vector gives me minus square root of 1/2. Row 2 of this vector plus row 2 of this vector gives me plus square root of 1/2. Okay, and that's basically what I see here. Okay, so this is the eigenvector, one of the eigenvectors of Sx. And what you can do, I think what you will do, is confirm that if I take this matrix Sx and multiply it by this vector, I'm going to get the same vector out, just multiplied by h bar over 2. So the result will be a vector pointing along the same direction, right? And what direction is that? So I have to orient myself along the basis kets, my basis alpha hat and beta hat, right? So this vector, okay, so if I wanted to represent this chi beta, right, it is minus 1/2, minus square root of 1/2 along alpha. So it's like down here, and plus square root of 1/2 along beta, which is over here, right? So this basis ket for x spin, right, in our original frame points like this. And if I multiply it by Sx, right, it's going to just scale this vector by the number minus h bar over 2. So it's still going to be parallel along this direction, just shorter and pointing in the opposite direction by minus h bar over 2. That's what we should see if we multiply this vector by Sx. Okay. So any questions about that? Yeah, go ahead.
But for the first shape of the vowels, is this supposed to be a 1 after?
It's actually not supposed to be a 1, although there's no difference. There's sort of like no difference mathematically between this shape 2 comma nothing and 2 comma 1. But what is different is that if I try to take the transpose of vowels, it won't do anything to it. It will leave it unchanged because it is Numpy will only transpose things that have like number, comma, number shape or more. It like will not transpose things that have like number, comma, nothing. I don't know what that is. It's something about how this vector is represented to NumPy. Okay. So we're getting close to the end of time. So let me just make a few remarks. You have a couple more questions, 4 more questions to be exact, and there's no new syntax really. Taking expectation values, you're going to sort of combine the syntax of taking dot products with taking, so I should say you're going to sort of like compound dot products to do expectation values. Because essentially what you can think of this expectation value is I'm going to first act on this ket with a matrix. So I'm going to do a dot between the matrix and the ket, and that's going to give me a new vector, which is going to have the same shape as the ket. And then I'm going to multiply, I'm going to dot the bra into that new ket. So this is the process of an expectation value. We're going to do lots of expectation values throughout class because they are very important in quantum mechanics. They relate to postulate 4. Right, they relate to what you expect will happen if I have like many states, many copies of some quantum system in some state described by this ket, and then I make a measurement of this observable Sx on each one individually and average the results. So we'll get some practice doing that with our basis kets of X and with the basis kets of Y. So let me also point out, this is not a typo here. This is not a typo, so pay close attention. In this case, question 5, I'm saying I'm going to use the basis kets of Sx that we just found from finding the eigenvectors in this expectation value, okay? That is one kind of situation you might find yourself in when you are in an eigenstate of the operator and you take an expectation value. That has one type of outcome. Now, question 6 is a little different. It says, let's say that I am in a state which is an eigenstate of Sy, but I am interested in the expectation value of Sz. Okay, so that is kind of a different situation. So just make sure that you are keeping track of the names of your kets with respect to each matrix, right? So we have ket X from the eigenvectors of Sx, and we have we're calling the kets of Sz something different. We're calling the kets of Sy something different. So any questions about that? That last piece might be a little confusing. Yeah.
I have a question about question 2.
Yes.
Do you want us to print the shape of each one in order to figure that out?
Yes, please. Yeah. Yes, please. They should have the same shape, but do print them all out to ensure that they do.
And then when we get the shape, do you just want the value that we get as the answer?
Mm-hmm. That's right.
Okay.
Yep. Yeah, so the questions that don't say explain your reasoning, you can literally just answer as concisely as it is possible to do, which in this case is you just write the shape. The shape is that's the answer. Explain your reasoning, right? I tried to give you that example, right? Answer is no, and the reasoning is we see that the results of multiplying these basis kets rotate them and change their length, which means they are not eigenstates. So that would be the reasoning. Okay. Finally, commutators. So there is some information which I believe we well, no, I don't think we really discussed in lecture yet, but this is actually something that we are going to reiterate in lecture. The interpretation of commutators in terms of what it means if the observables associated with, in this case, operator A hat are compatible with the observables associated with operator B hat. So this is an attempt to sort of close the loop on this business of why the outcomes of the Stern-Gerlach experiment with multiple spin boxes, SX, SY, or SC, SX, or whatever, give you the results that they do. So the last, taking commutators is really just a matter of multiplying matrices together. So again, you know the syntax. You can do np dot matrix 1, matrix 2, just like this. And also, even simpler syntax, you can use the ampersand sign to do matrix multiplication. So that's it. Okay, any questions? So folks that are in lecture, what we will do is we'll continue to kind of work with these spin matrices and spin states for another day or two, yeah, for lab folks, this will probably be the end of spin. Until experiment 21, yeah. Okay, awesome. All right, great work, everybody. Not for lecture. Lecture will, yeah. Thank you, though.